Okay, so far we have showed a result for the existence of solutions for of the projection. So I formalize the theorem as above, as here. So let's say X is a point in the B star space. Sorry, I should say. I start with the B star space, and I also have an orthonormal set or linear independent set will be sufficient. And then given any X, there exists a vector A in Rn such that f of A defined as the sum from 1 to n of AI, EI can be minimized. Okay, so let me specify this more clearly that I denote this minimizer as A star. So that means f of A star is the minimum value of f of A for A in Rn. Okay, so this is what we proved by the derivation above. Okay, so what this tells us, it says that as long as I have a B star space and I have a linear subspace, finite dimensional linear subspace, which is spanned by these vectors, or if you just know that it's a finite dimensional linear subspace of X, then you know you can find a basis for that some linear subspace. And in this case, you're always able to find the minimizer by denoted by this A star. Okay, so what do I mean by that is, say you generally have a X as your B star space, and you have, so this is a whole B star space X, and you have a finite dimensional linear subspace, which could be just spanned by some E1, E2, or undimensional, unlinear independent vectors. Then for any X, you'll be able to find a unique point on this linear subspace, and this point is written as AI, EI, I is from 1 to n. Okay? And these EIs are the linearly independent sets that form this or span this linear subspace. Okay, so that's for the finite dimensional case. So usually when we can rewrite this as a problem as follows, if you were not given the linear independent set here, but directly given the finite dimensional linear subspace M, say this space is M. I only know that, I don't know where the E1, E2s. So I could also form this optimization problem as finding the infimum of X minus Y, where Y is from this linear subspace M. But what this theorem tells us, or what the derivation we had above, is that this infimum actually can be replaced by maximum, because if M is finite dimensional, then we'll be able to find a minimizer. Okay, so we can actually find this minimum, not maximum. We can actually find this point. So in this case, I will call. So from graph, it will be pretty clear. We have this X, this is our M, and then we'll be able to find some Y here, such that this distance here between X and Y is actually the distance between X and the whole space M. So the X minus Y is actually the minimum, or I call this Y star. Is actually the distance between the point X and the subspace M. Okay, And then in this case, we'll be able to just say, because this is just like the distance between x and y. This is like the distance between x and m. Okay, so we can directly claim that such a minimizer must be unique. We must be able to, such a minimizer must exist. So we must be able to find such a y star. Okay, so we answered the question about the existence of such kind of minimizer. Another question is if this minimizer is unique or not. Okay. In general, this minimizer is not necessarily unique, but we're going to give a sufficient condition to show that such a minimizer is unique. So in this case, we'll call, say, we have a B star space. So I have a B star space X, and that has a norm. Okay, and then we call strictly convex. We call this B star space strictly convex if for any if for any x and y where x is not equal to y and that the norm of x and y are both equal to 1, then there is the strict linear combination, strict convex combination of x and y, which is denoted by this plus lambda y. We know this is a convex combination of x and y, right? But by strict convex combination, we say that lambda is strictly between 0 and 1, not equal to 0 or 1. If this is always less than 1 for any lambda like this, then we can claim, we call this B star space strictly convex. Okay, so let's see what this actually means. You can imagine that if x and y both have the length 1 or the norm 1 and they're not equal, that means these are two different points on the sphere, unit sphere inside X. And then for any 2 points on the unit, different points on the unit sphere of X, their strict convex combination is inside the sphere or inside the ball. Then, because its length is less than 1, strictly less than 1, then we can claim this is strictly convex set, strictly convex space. Okay, so you can imagine that generally we would expect to have strictly convex set because, for example, we have a ball like this, and we have 2 different points, x and y, and then apparently when connect this to any 2 points in between will fall inside this ball. But this is only a very simple example. We actually cannot expect this to hold for any B star space. For example, if I have just x equals to R2, like I had on the left, and I define my norm to be the 1 norm. This is my 1 norm, meaning that for any vector x, I will just have the absolute value of the components of x, because x is x1, x2. Then I will not be able to get strictly convex space, because in this case, I know this is x1, this is x2. This diamond shows what points have the norm 1. Okay, because you can see all the points on this diamond, they all have the norm 1. So if I pick up any 2 points, like here, and also here, this is my x, this is my y, and I make a connection between them, you can see they're still on the boundary. Their norms are still equal to 1 for any points on the line segment. So in this case, this is not a strictly convex set. Okay, but for 2 norm, if I replace this by 2 norm, that will be what we have on the left. If I have this standard 2 norm, then this is the strictly convex set. So that's the difference. Okay. we'll see several more examples later. Okay. Okay, so the theorem here says that if we have strict convex B-star space X, then we can guarantee the minimizer we found earlier is actually unique. Okay, so the setup here is identical to the one we had before, except that we also added this strict convexity for the X. So this is again the basis or the linear independent set, and for any X we can find a unique vector A which contains A1 through AM, such that this functional is minimized. Okay, and the only thing we need to do is just to show uniqueness. Okay, we already showed the existence earlier. Okay, suppose A, B are both minimizers. Of F. So in this case, I know that I can denote two vectors. One is written as the linear combination of EIs using A as the coefficients, which is E, AI, EI, as from 1 to n. And also I can have the Z, that is the sum, again, linear combination of the EIs, but using BI as the minimizer, as the coefficients. So that means I find this Y and Z. They are both points in the span of the E1 through En, and they have this equal distance to the point X. Okay, so and you know this distance is just the distance between X and the space M. Okay, and this space M is the M is actually the span of E1 through En. So I can let for simplicity, let's say I use R to denote the distance between X and M, which you know this is just the minimum value of FA. And in this case, you know this value actually is equal to the distance between X and Y, and also the distance between X and Z, since Z, Y, and Z are actually obtained using the coefficients A and B. Okay, so you know this. And now from here, you can say that I have, I can consider this. I know that Y and Z have the same distance to X. But how about the convex combination of Y and Z? So I look at this X minus a strict convex combination of Y and Z. So it's 1 minus lambda times Y plus lambda times Z. and I divided by r. So I look at this. I want to show that this is actually strictly less than 1. And then from there I can get that the y and z must be equal. Okay, and how do we show that? It's pretty straightforward. I just make some different combinations of this. I can split this x into 1 minus lambda times x and lambda times x, and then combine one with this and the other one with this. Okay, so I'll get 1 minus lambda times x minus y plus lambda times x minus z. Okay, and now from here I can say I can put this r inside. I have a 1 minus lambda because r is positive, right? And I have that 1 x minus y over r plus lambda times x minus z over r. Okay, I'm assuming that the minimizer, the x actually outside of this M, because if x is already inside M, then that means x can be uniquely represented by E1 through En, and there's no way to get two different minimizers, right? They have to be just x itself. Okay, and in this case, if x is outside, then the r must be positive, then I can write this. Okay, now you can notice that this here, as we showed earlier, the r is just the norm of the two. So this first term here, it will be just the x minus y over x minus y, right? So that means this one actually has a norm 1. That means the norm of this is actually equal to 1. Okay, similarly, the norm of this is actually equal to 1. So I do have 2 points that are on the sphere, unit sphere in the space X, which is this one and this one. And I make a combination of them, strict convex combination of them. And because of strict convexity of the space X, this is supposed to be less than 1. Okay, this is supposed to be less than 1. So this is less than 1 means that I can have, with lambda, I can just multiply r on both sides. I'll get this. Okay, and from here I will get a contradiction because both of this y and z, they're from the space M. So the combination of them will be still in M. So I found this point, which has the distance to x less than r, but r was supposed to be the distance between the space X and M. That's the smallest value I can get if I put some point here belonging to R, belonging to M. That's where the contradiction is. Okay, so that means the y and z must be equal to avoid this. When they are equal, then this is essentially just a y, and also essentially just z's themselves. In this case, we will not get contradiction. Okay, so if these two both minimizers of f, but the different, so yeah, see that if you want to prove this by contradiction, then this is a contradiction to the definition of R. Okay, and we claim that A and B must be equal. So A must be equal to B, and that means the minimizer must be unique. Okay, let's look at the example. A popular example for strictly convex set in functional analysis or in measure theory is this. Say I have this LP space where P is strictly between 1 and positive infinity. Okay, this is a strictly convex. Okay, and this also means that if you have a linear subspace in this LP space, then any point in the space will have a unique, I would say, projection onto the subspace. Okay, it will have a unique projection. So why this is a strict convex set? It's because here this omega is the domain where the functions are defined in the space. So this is actually just the space of functions defined on omega, and the mu tells you the measure for the omega. So the simplest example is that you have the R, and this mu is just the big measure. Okay, and why this is a convex set? This is because of the norm defined in RP. Recall that the norm defined on RP we say is the P norm, right? The property of the P norm is that by using the Minkowski's inequality, we know this is true. This is always true, right? But in which case this inequality becomes equality. This one becomes equality. Apparently, when U or V is 0, then this is equality, right? But we're more concerned about strict convexity, so we'll be considering the case where U and V are both non-zeros, because we want to show that if U and we want to show something like that. We want to show that this and this. When we make a convex combination, I want to show that this is actually less than 1 for lambda between 0 and 1. Okay, if one of them is 0, then it's nothing to do over there. Okay, so to the P here. So we'll consider the case where U and V are both non-zeros. So now assume that they're both non-zeros, and assume that U and V they both have the P norm equal to 1 as a setup of a strict convexity. And if they're not equal, or I would say if I want this equality for this one to hold, at the same time I want the U and V are non-zero, the only possible case is that U must be equal to some constant times V, right? Then C is positive. This is the only case. If U and V are both non-zero and this equality here holds, the only possibility is that there exists some constant C such that U is equal to C times V. Okay? And in this case, apparently, when you have U and V both having the norm 1, then that just means that the U and V are equal. There's only one way, because if this holds and this holds, that just means U and V are equal, because you can just scale one of them, and then you realize C is just equal to 1. Okay, so that also means that if you have this, and at the same time you want U not equal to V, then this cannot happen. So you have non-zero U and V such that this is true, then this cannot happen. I cannot write U as C times V. And if that's not the case, then I can never get equality here. I will only have strict less than. So to summarize, what I have here is that if we assume that the P norm of U and P norm of V are equal to 1, and U is not equal to V, then I can claim that the U plus VP will be strictly less than, I would say, let's say, I'll look at the 1 minus lambda times U plus 1 lambda times V. When I look at this, I'll realize that there's no way that 1 minus lambda times U plus or is equal to C times lambda times V. As I showed earlier, if the U norm is equal to 1, the V norm is equal to 1, then I will have to have this, or the U is equal to some constant times V. Now the constant just becomes this divided by that. Okay, but anyway, that U must be proportional to V almost everywhere for the same constant if I want the equality to hold. But if that's not the case, if I already have these two, then that means this can never happen. And this never happen means that I can only have the strictly less than the norm of 1 minus lambda U P plus lambda times VP. And because of the homogeneity of norms, I can pull out the 1 minus lambda lambda. So it's just 1 minus lambda times the P norm of U plus lambda times the P norm of V. But both of these two is equal to 1. They're equal to 1. So that means this is just equal to 1. Okay, because adding these two is just giving me 1. So that's why this space is strictly convex. Okay, but recall that this must be P greater than 1, strictly greater than 1, and not infinity. Okay, let's look at the case where P equals to 1. So this is actually pretty much like the case we considered earlier. When we have the R2 space, when we define the 1 norm, then we will not have a strict convex space. One example for this is, let's say I have L1 of the interval 0, 1. So this is only L1 integrable function, or the Lebesgue integrable function over the interval 0, 1. So I can define 2 points in the space. One is the function constantly equal to 1. The other one is the function equal to 2t. Okay. So you know in this case, if I draw the picture, 0, 1, 2. So I know the x is just a constant function, it's t. And the y is this function. So I can take an average of them. So the 1/2 times xt plus 1/2 times yt, just giving me 1/2 plus t, and that is just this line. Okay, just this line. And apparently, if you take the integral of this function, you know this is just the same as taking the integral for each of them. You even can look at this by you can see this by looking at the areas, because this is just equal to 1 as we define here, and this also equal to 1 is the area of the triangle, and you take the average of them, it's still getting 1. So that means this, although it's a strict convex combination of the two functions or 2 points in this space, but actually the combination is also has the norm 1. Okay, so that means this L1 space is not strictly convex. And similarly, you can show that our infinite space is not strictly convex. Okay, let's see another example. How about this space? This norm is a common maximum norm we had, right? We define the x norm of x to be the maximum of, say, it's f here, to be the maximum of fx. Okay, this is also not strictly convex. The reason is you look at these two functions. Let's just say that c0, 1. And norm is just the norm defined on this space. And then in this case, we say xt is constantly equal to 1. The yt is equal to t. So in this case, 0, 1, t. Now this is the 1. So x is this constant function again. Y is this function. So the middle point between these two, 1/2 times x plus y, xt, yt, just equal to this. But apparently the maximum norm, or the maximum value of this function here is also 1. So I do have a strict convex combination of the two, but if I take the norm of this, it's still equal to 1, just the same as the x and y themselves. Okay? So this also verifies that this is not a strictly convex set, a strict convex space. Okay, so that's all about that. Now we have an interesting and sometimes very useful characterization of the unit sphere in the B star space. Let X be a B star space. Then the X is finite dimensional if and only if the unit sphere S is sequentially compact. Okay, so we actually know one dimension. One direction. If you know this is finite dimensional, then apparently this is strictly sequentially compact. The reason is if it's finite dimensional, we basically can treat this, or this is actually homomorphic to the space Rn, where n is the dimension, since n is a finite number. And in this case, this is actually the unit sphere in Rn. And we know the unit sphere in Rn is actually compact and also sequentially compact. Okay, so from this to this is pretty straightforward. And the question is, why we can also use this as a criterion to check if X is finite dimensional or infinite dimensional. Okay, and this is a very simple condition. You just check the unit sphere. If it is sequentially compact, then the space must be finite dimensional. Otherwise, it's not. Okay, so I will just prove this direction. Okay, to prove this, let's say that I will start from, we'll pick up any point. Let's do this. Suppose I already have a endpoints in S. I have endpoints that are in S. Say, let me write it this way. Okay, and because this is not, if X is not finite dimensional, then what I will have is, say, let me say this first. Suppose X is not finite dimensional. And then I consider the x1 through xn, they're from the unit sphere. Then the span of x1 through xn must be a proper subspace of X. The reason is, if I denote this by Mn, this must be a proper subspace of X. The reason if it is a subspace, if it is equal to X, then I can actually the X is actually equal to the span of this. That means this is the finite dimensional space because I only have finite many vectors in here. So that means I can span everything in X by using this. So that means X is a finite dimensional, and that is a contradiction to what I have. So if it's not finite dimensional, then no matter what vectors I choose from the unit sphere, the span of these vectors must be a proper subspace of X. And it is proper subspace of X means that there exists some Y that is in X, but it is not in Mn. Okay, and because of that, because we show that any Y, we can find a unique point in the Mn. Such that the Y, the norm of Y minus Z is actually the minimum, Z. It's the minimum of the value for x in M, or the distance between y and mn, sorry. Right? So in this case, I can just define, so graphically this is pretty straightforward. This is just mn, and I have y outside, and this z is right here inside mn. So the distance here between y and z is actually the distance between y and mn. So we showed it before. I know this z must exist. Okay, this is exists. So now we define the xn plus 1 to be y minus c divided by y minus normal y minus c. And apparently the xn plus 1, by the way, this must be positive because the y is not inside mn, right? So I know that's the norm of xn plus 1 is equal to 1, so that also means xn plus 1 is actually in S. Okay, and then I can put this xn plus 1 together with the previous xn, so x1 through xn. And again, because x is not finite dimensional, I can again show m plus 1, which is just including this xn plus 1 into here. I got mn plus 1. It's still not, it's still a proper subspace, and I can continue doing so. So I can get generate sequence. By repeating this, we obtain a sequence x1, x2, and so forth. They are all in S. But because S is sequentially compact, I'm supposed to get a convergent subsequence, right? However, when you look at the construction we had earlier, if I get x1, then I do get x2 by doing this procedure, I realize that the distance between x1 and x2 must be greater than or equal to 1. Since if I have this as my x2, this is my x1, or in this particular case, as you can see, when I look at the distance between the xn plus 1 and any other point x, say x xi, say now xn plus 1 minus xi, when I look at the distance between these two, I realize that it's nothing but just so we show the word is y minus z over y minus d minus xi, right? This is how I define xn plus 1. And then I can see that it's just make a common denominator. I will have y minus z plus y minus z xi. Okay, and you know that this one, the z is from the Mn space. Xi is from the Mn space as well because the Mn is spanned by those. And there is a linear combination of the two, so it's still in Mn. So this whole thing is in Mn. And I know that the distance between y and Mn, this is the bigger, this is the bigger than equal to, so this is equal to y minus z, y z psi. I pull out the denominator. I know that the numerator must be bigger than the denominator because this is actually where I can find this is the distance between y and Mn. And this must be greater than or equal to the distance, since this is the point in Mn. Okay, so that tells me that this must be greater than or equal to 1. So I show that this is greater than or equal to 1 for any I from 1 to n. Okay, for every one I got, its distance to any previous point is bigger than or equal to 1. So this is how I got this sequence. And there's no way that I can get a convergent subsequence because the gap, the distance between any 2 points in this sequence is bigger than or equal to 1. So this contradicts to, so there is no convergent subsequence of this X sequence here, which contradicts to as being sequentially compact. Okay, so this is a pretty important result. Sorry, we can check the dimensionality, or if it's finite dimensional or not, just by checking the sequential compactness of the sphere. Okay, so the last result is due to Rees. Okay, so what it says is this, suppose I have a B star space. Okay, and X is not is a proper subspace. Proper closed subspace, say. Okay, here this X naught is not necessarily like the M ends above. It could be infinite dimensional. Could be infinite dimensional. Okay, and in this case, we can get something similar to the one above, but a little bit different is that we cannot really strictly get some point, or I would say getting a vector that is popping out of this space X naught with length 1. So more specifically, what I only have is there exists, actually say there for any, what I can claim is for any epsilon between 0 and 1, there exists some y in the space X such that the norm of y equals to 1, and the distance between y and x is bigger than or equal to 1 minus epsilon for any x in the subspace. Okay, so in other words, I have this x naught, but this could be infinite dimensional, so I lose some of the results properties we had earlier, but in this case, I can still show that for any epsilon, there exists a y that is outside of the x naught, such that the length of y is equal to 1, and the distance between y and any points on the x naught is bigger than or equal to 1 minus epsilon. Okay, or at least that also means the distance between y and x naught is bigger than or equal to 1 minus epsilon. Okay, see how to prove this. Because the x naught is a proper subspace of x, so I know that there exists some z that is in x but not in x naught. Okay, and I also denote this r to be the infimum of the point, the distance between z and any point in x naught. And I know that this must be greater than 0, because if it's equal to 0, then that means I can find a sequence of points in x naught that convert to z. But the x naught space is closed, and that also means z is in x naught. That is contradiction to what I have here. Okay, so now I know that this must be greater than 0. So when it's greater than 0, I can divide it. Right? You can make the denominator, make it as a denominator. Okay, so now for any epsilon in 0 and 1, I know there exists some eta greater than 0. I'm going to specify what this eta needs to be, but I know that there must exist some eta such that, and also x naught such that r is between the distance, sorry, r is less than this, but it's also less than r plus eta. The reason of this is because the r is defined as the infimum. So that means I can, for any eta, I can find a x naught such that z minus x naught is actually between is bigger than or equal to r. I only need bigger than, say, bigger than or equal to r, but less than this. This is because of the infimum we used in the definition for r, right? So I have this. And then in this case, I can just find my y. I like my y to be the z minus x naught divided by z minus x naught. So apparently the normal y is equal to 1. And I'm going to show that the distance between y at any point x from the space x naught is greater than or equal to 1 minus epsilon. Okay, and in this case, I will tell you how small I need this epsilon to be, this eta to be. Okay, so now let's say the y minus x. I know that by definition of y is just this. Okay, and again, I make common denominator, which is z minus x naught plus z minus x naught x divided by z minus x naught. And I can pull out this denominator. Okay, so apparently the numerator here, since x naught is in the space x naught here, this x is from the space x naught as well. So this must be inside x naught. So I know that this distance must be bigger than or equal to r. Okay, at the same time, I know that this is smaller than r plus eta. So in total, I know this must be greater than r over r plus eta. And this is true for any x in x naught. Okay, if I want this to be greater than or equal to 1 minus epsilon, I just need to make sure that this is greater than or equal to 1 minus epsilon. Or for simplicity, I can just set this to be 1 over 1 minus epsilon and solve for the eta. Okay, so that we can just solve r over r plus eta to be 1 minus epsilon. Then I will get epsilon equal to epsilon r over 1 minus epsilon. So you can set any epsilon, any eta equal to or less than this number, less than or equal to this number, then I can show that this is always greater than or equal to this, which is equal to 1 minus epsilon for any x in here. That's the Ritz lemma. All right. Okay, now we're going to consider more about the convex set. We mentioned something about it earlier, but actually there are lots of interesting structure that we can explore, or property we can explore if the space is convex or a set is convex. We're going to consider convex sets and fixed points. Okay, so we're going to introduce several more fixed points theorem in this section. Okay, so definition for convex set. I think this probably many of you have been pretty familiar with, is that if X is a linear space, and the E is a subset of X, it's called convex if for any 2 points from the E and any lambda between 0 and 1, there is 1 minus lambda times x plus lambda times y is in E. Okay, so basically what this means is you have this as your E, and for any 2 points, x and y, you make a line segment. This is the convex combination we show here. If all the line segments are in E, then you can call this E a convex set. Counterexample would be this. So for example, if the E is like that, then if you choose 2 points here, then it could happen that the line segment is not completely in E. Okay, although for some other points they're in, but for a set E to be convex, it requires all the points, all the pairs of points. When you make a line segment between them, you get the whole line segment inside E. So that's why this is not a convex set, but this is one. Okay. A property of a convex set is that when you take intersection of convex sets, you will still get a convex set. Okay, so let's say if all these are, I have a bunch of convex sets, could have finite many of them or infinite many of them. Okay, and even uncountably many of them. If they're all convex, then I take an intersection of them, is still convex. This one is still convex set. The reason is you pick up any 2 points, x and y, from this intersection, you know that since it is in the intersection, they must be inside every one of them. And if it's inside every one of them, that means the line segment between them will be inside every one of them. So that means this line segment of them will be inside the intersection. So this shows that this is actually also a convex set. Making intersection of convex sets will give us a convex set. But for union, it's not necessarily true. You take the union of 2 convex sets, it's not necessarily convex. Okay. For example, you have a convex set like this and another convex set like this. Apparently, it's not necessarily convex. If I draw this in this way, maybe you take the union of them two, union of the two, then this may not be inside. But if you take the intersection, then this is still convex set. Okay, convex Hall. So what is it called a convex Hall? I think that suppose X is a linear space, and E is just some set of X, not necessarily convex. I can make a convex Hall of E. What that means is I can consider the family of convex sets denoted by F. So it's just a collection of subsets of X, which contains F, which contains E. At the same time, F is convex. Okay, it just means it's just F is just a collection of all the convex sets that contain E. Okay, and this by taking intersection of those F, we call it the convex Hall, which is the intersection of all those F where F is from this family. Okay. So what this actually means is you can imagine this convex Hall is just giving you the smallest convex set that contains E, right? As I'll define here. Some typical example is like, say for example, I have E like that, then the convex Hall will be just like this. Okay, just contain this. It will be just the whole thing here. Okay, or if your E is just a bunch of points, like this, then the convex Hall will be just this. Okay, so sometimes convex Hall is also called convex envelope. It's just the smallest convex set that can include the set E. Okay, that's the convex Hall. Okay, so I'm going to make a more mathematical characterization of convex Hall. Let X be in a linear space. Then, actually, the convex Hall of E is just all the convex combination of points inside E. So I write this as AI xi i's from 1 to n, where the xi's are from the space, sorry, the set E, and the n is arbitrary. You can pick up arbitrary many points from E and make a convex combination of them. So what the convex combination means is to get those coefficients a1 through an, which sum to 1, and each one of them is greater than or equal to 0. Okay, this is the convex combination for n points, but the n can be arbitrary. N can be arbitrary. So I put in here. So that means you pick up arbitrary number of points from E, and you make a convex combination of them and throw it into this set. And the collection of such a set, the collection of such points is called the convex Hall. Okay. I'll claim this, and to prove that, pretty straightforward. I just call, say, on my right hand side, I call it S. Then the proof is that I want to show the convex Hall E is inside S. So I want to first show this. To show this, let's say for any, let's say, first of all, the S itself is convex. As you can see, because this is the way you make these are the elements in S. So you can see that when you make a convex combination of the points, 2 points, each one like this, then it will be still inside S. So that means S is convex. And also apparently when you just pick up any point from E, you do not make any convex combination. You just say I have the 1 times X, where X is, itself is from E, then apparently the E is inside S. So that means S is convex and the E belongs to, or is contained in S. And this means that the S is inside the family we talked about earlier, right? And then this means that the convex Hall of E must be contained in S, because convex Hall is the smallest convex set containing E, and S is just some convex set containing E. Okay, that's why this is true. The other direction is also straightforward. Okay, I can show that the S actually inside the convex Hall of E as well. To show that, I just need to show that any element in S is also in E. Okay, and that's obvious. As you can see, S contains points like this. So if I have the xi's from E, then this must be contained in any convex set containing E. So that means this must be in F for, sorry, this point must be in F for any F in the family I talked about earlier. Okay, for any point in S, I show that it is contained in F. Okay, so that means S. So let's say for any point S, we know S belongs to F for any F in the family, and this means that S is actually contained in F for any F inside the family. And this tells us that S is actually the smallest convex set. And this just means that S, apparently the convex Hall is also in F. So if I replace this by convex Hall of E, then I will have S is contained in the convex Hall of E. And previously we showed the convex Hall of E is also in S. So combining these two just tells us that S is equal to convex Hall of E. Okay, so this is the way to characterize what the convex Hall of E looks like. Right? Now, the reason why I define convex Hall is that we can introduce this so-called Minkowski's functional. Minkowski functional. Okay, so suppose X is a linear space. C is a convex subset of X. It's convex. The contains 0. Then we define a functional. It's a mapping defined on X to the set of real numbers as follows. For each point in the space X, I define this to be the infimum of the real numbers lambda, such that X over lambda is in C. Okay, so what this means, you can try to draw pictures yourself to have a better understanding. So roughly what this means is, suppose we have the C here. Sorry, you have the C here which contains 0. So this is my C. This is convex. And then for any X, I want to see how what is the smallest number lambda I can use to scale this X down, such that it's eventually inside C. So as you can see, in this case, I probably need this lambda to be about 2. Right? Lambda is about 2. Anything bigger than 2 will be fine. Say you divide this by 100, divide by X by 100, then still it will be inside the C. But what is the smallest possible number you can use to divide the X? That is the number P of X. It tells you the scalar lambda. But this is taken as the infimum, not actually the minimum. So let's be careful about that. Okay, this is called, P is called the Minkowski functional. Of C. Sometimes it's also called gauge function. Okay, but I think this is more used though. Okay, so I'm going to, apparently when we define this, we need, it has several interesting properties that we can use later. So I'm going to list some of them here. So let's, again, X be a linear space. C is the convex subset of X containing 0, as we set up above. Then the Minkowski's functional satisfies the following statements, has the following properties. The first is that the Px must be non-negative, and also if you look at 0, it's equal to 0. Second property is, let's say this is the first property. Second property is that the P of lambda x equals to lambda P of x for any lambda greater than 0 and any x in the space X. So this means that P is actually positive homogeneous. The third one is that the P is subadditive. Okay, it's pretty much like what we need for a sublinear functional, as we introduced before. Okay, the proof. The first one is obviously true because this is defined as the infimum of non-negative or positive numbers. So this eventually must be greater than or equal to 0. right? So that's why this must be greater than or equal to 0. And it could be infinity. It's because in which case it will be infinity. Let's say I have, say this is my C. This is the 0. So if I have a point like here, then no matter how large the number I divide, this is my x, no matter how large the lambda is, there's no way that this is the inside for lambda greater than 0. There's no way for this one to be inside C. So lambda could be eventually infinity. There's no way to find it. So that's why this is also possible. Okay, so and anything between could be possible, but it's always greater than or equal to 0. And if when we look at 0, since 0 is already in C, so you don't need to divide anything. 0 divided by lambda is always in C because it's always equal to 0. So when you take the infimum for lambda, you just get 0. That's why this is true. So the first one is pretty easy to check. Second one, again, it's pretty easy to check. If you have, don't be confused with this lambda. Maybe I used A here. A. Okay. Then you can easily show that's also true because you just need to scale. If you have ax inside of x, then we'll scale this down by lambda. You need to also multiply this by a. Okay, so that's pretty easy to show the second one. Third one is a little bit tricky, so let's see how to do that. I'm going to show that for any epsilon greater than 0. I know that due to the definition for the Minkowski, Minkowski functional, let's say there exists lambda 1 greater than 0, and also exists lambda 2 greater than 0, such that the px is less than or equal to lambda 1 less than px plus half epsilon. This reason is because the px is defined as the infimum of the lambda, right? So for the fixed x, I can find this lambda 1, which is between that. That's because of the infimum definition, right? Similarly, I can have the py less than or equal to lambda 2 is between this. That's how my lambda 2 is found. Okay, and now I want to first show that the lambda 1 plus lambda 2 will be or x plus y divided by lambda 1 plus lambda 2. I want to first show that this is in C. I want to show that this is in C. Okay, I want to first show this. And if I can show this, that means the p of x plus y will be less than or equal to lambda 1 plus lambda 2, because this is supposed to be the infimum of lambda such that when it is divided by some lambda here, you get it to C. So now if the lambda 1 plus lambda 2 works, that means lambda 1 plus lambda 2 must be bigger than or equal to the infimum. Okay, but how do I show that this is in C? I can see that this is actually a convex combination of 2 points, where this is lambda 1 plus lambda 2, lambda 2, lambda 1 plus lambda 2. I know this is like a combination coefficients. And for the here, I'll have lambda 1 x. And for here, I will have the y over lambda 2. Okay, as long as I can now I have the convex combination using these coefficients, convex combination of these 2 points. Well, because this is in C, sorry, I should say that the lambda 1 was chosen such that x over lambda 1, how should I say this, is in C. No, also y divided by lambda 2 is in C. Because of the definition for that, the px is a infimum, so I can find some lambda 1. But this lambda 1 also makes sure that it is inside this set. So that means x over lambda 1 is in C. Similarly for the lambda 2. Okay, so I can do this, and that means this is in C, this is in C, in the convex combination of the two is in C. But the convex combination of the two, as you can see, you cancel this two, you cancel this two. That's essentially just this. That's why this is in C. Okay, it's in C, then implies that. Okay, and from here I can say that this is because of the lambda 1, lambda 2, there lambda 1 is smaller than px plus epsilon over 2, and the lambda 2 is less than py plus epsilon over 2. And the right hand side will be equal to px plus py plus epsilon. Now I show that this is less than or equal to this for any epsilon greater than 0. So that just means that this is less than or equal to this. Okay, so as epsilon is arbitrary, we know that px plus y is less than or equal to px plus py, and this finished the proof for the third one.